All right, to start Unit 7, we are going to start by talking about the tangent function and all of the important things about it. We're also going to learn what the graph of a tangent function looks like and how to do the transformations on it. All right, the tangent function represents the slope of the terminal ray of an angle, theta. F of theta equals tangent x is equal to sine theta over cosine theta. That's by definition that the sine theta equals over cosine theta equals the tangent theta. That is the definition of tangent. It's the sine of the angle divided by the cosine of the angle. All right, tangent of theta is equal to 0 whenever sine theta is equal to 0, because we would have 0 divided by some number. 0 divided by anything other than 0 is 0. And tangent theta is not defined or undefined when cosine theta equals 0. Because if cosine theta equals 0 here, then we're going to have the division by 0 error. And remember, that's an undefined property. We cannot divide by 0. Now, the domain for the tangent function is all real numbers except that x cannot equal pi over 2 plus pi k, where k is an integer. So in other words, what we're going to find, if we look right down here, the period is pi. So it's going to repeat itself every pi. It's going to repeat the cycle every pi. And if you have and we do have a vertical asymptote where it's not defined. So we have a vertical asymptote when cosine theta equals 0, which is at pi over 2, and then it's going to occur every single time we add pi to that. So it's going to occur at pi over 2, at 3 pi over 2 when we add pi. When we add pi again, it'll be at 5 pi over 2. What you're going to find is it's going to be undefined at all the odd values of pi over 2. The even values of pi over 2 of course are going to reduce, but all the odd powers of pi over 2, you're going to have a vertical asymptote there, and that's what it means where k is an integer. Now the range for the tangent function is all real numbers. In other words, it's going to go from negative infinity all the way up to positive infinity. Notice this changes from what we had with sine and cosine. With sine and cosine, we still had the domain of all real numbers, but we had a range that went from -1 to +1. This one includes all real numbers for the range as well as the domain, except for this exception. Now, as I mentioned, the period is pi, and tangent functions can be transformed in much the same way that we did with the sine and cosine. Notice we've got a very, very similar value or equation right here where all the things mean exactly the same thing. The A means amplitude, although the amplitude really doesn't affect this one much. It's just going to mean that it's going to grow a little faster going up and it's going to go down a little faster going down. It's not going to be as noticeable as it is with the sine and cosine values. The B is going to be the big thing where it's going to change the period, which means it's going to change how far apart these vertical asymptotes are. The C, once again, is going to be a horizontal shift, so that means you're going to move that center point over one way or the other, and then you're going to go on either side of that and find where the vertical asymptotes are, and you can go and graph from there. And then, of course, the plus D is just the vertical shift, up or down. Now, notice with this one, we talked about with the sine and cosine. Remember, I kept telling you guys the new period was my equation. The new period equals the old period divided by b. Well, this is kind of where that comes into play, because the period for this one, since the old period is pi, the new period for the tangent function is going to be pi divided by b, since pi is the old period. So the new period is going to be just pi, not 2 pi, divided by b, because the original period of the tangent function is going to be pi. All right, so here's a place where definitions matter. and you need to know what they are. Okay, it says find an exact value for the slope of the terminal ray of an angle theta when theta equals 7 pi over 6 and when theta equals 5 pi over 3. Now, the whole reason why this is important is because if you don't know what the slope of the terminal ray is, you're going to miss a really easy set of points with this problem. Now, let's go back one slide for just a second here, and the tangent function represents the slope of the terminal ray of an angle. What that means is this. What that means is this. If you've got a circle and you have a terminal side of an angle, so remember, an angle in standard position has its initial side along the positive x-axis, and then you've got some angle going off over here. That is the terminal ray. So what we're looking at is the slope of the terminal ray. Well, it kind of goes back to the definition here. Remember what sine theta always equates with on your points. It's always going to be your y. Cosine's always going to be your x. Well, what is y over x? Well, it's tangent, but what we really have here when we consider that we're starting at the origin and we've got the xy right here, is we've got the slope function, because we're literally taking y minus 0 over x minus 0. So we end up with y over x is the slope of that angle. So there's your x, there's your y. Y over x in this case represents the slope of this angle. Now understand, this is not this angle. It's not this angle over here. It's always going to be the slope of the angle, or sorry, the slope based on the closest x-axis. In other words, it's over in quadrant 2, it's over the negative x-axis. If your terminal side was over here, it would be with the positive x-axis. If it's down here, still with the positive x-axis, down here with the negative x-axis. But either way, when you find the tangent, what that value is telling you is it's telling you the angle, it's telling you the slope of the terminal ray that's based off of that angle. I'm sorry, I said angle. It does not tell you the angle, it tells you the slope. So this is going to tell you the slope of this line right here, which is how much the y changes over how much the x changes. And since we're basing the slope from 0, 0, it becomes this right here, even though it's technically just y over x. All right, so when they ask you to find the slope of the terminal ray of an angle, when they ask you to find that, all you need to think of is tangent theta. So you're finding an exact value for tangent theta when theta equals 7 pi over 6 and when theta equals 5 pi over 3. So if we want to find tangent of, and we can actually go ahead and plug our angle in here, we're going to end up doing sine of 7 pi over 6 divided by cosine of 7 pi over 6. All right, and when we do that, 7 pi over 6 remember, is in quadrant 3. So both sine and cosine, both your x and your y values, are going to be negative. And what do we know about our values? Well, if you remember your unit circle, which you have to, you should not have to look back at the unit circle for this. These are values you should know by memory or be able to easily find out. Now, if you remember the little trick I showed you, look at the cosine value. If it's a divided by 6, it's going to be a square root of 3 over 2 every single time, as long as that angle is reduced. If that was 8 pi over 6, you don't use this rule. You reduce it and then use the rule. But since we've got cosine of 7 pi over 6, and 7 pi over 6 is reduced as much as possible, we've got a 6 in the denominator. That means we're going to have a square root of 3 over 3. Since it's in quadrant 3, it's going to be a negative. And with the sine 7 pi over 6, well, 7 pi over 6, if our cosine is a positive, or sorry, a square root of 3 over 2, then our sine for that same angle has to be 1/2 because they always come together in pairs. Since it's in quadrant 3, we know our y value, otherwise known as our sine value, is going to be negative. So we end up with a negative divided by a negative, which is going to give us a positive value. And we're going to have 1/2 divided by square root of 3 over 2. Keep, change, flip. We're going to have 2 over the square root of 3. The 2's are going to cancel, and we end up with 1 over the square root of 3. If this is a free response question, you can leave it just like that. If it's a multiple choice, you may have to go ahead and rationalize that denominator. So you end up getting the square root of 3 over 3. So the square root over 3, square root of 3 over 3 is the tangent of 7 pi over 6. All right, so let's do the same thing with the 5 pi over 3. So tangent of 5 pi over 3. Now, you may even want to pause this and try the second one by yourself and then see if you got the right answer. Give it a try. All right, so we got the sine 5 pi over 3 over cosine 5 pi over 3 using that same little trick. Where do we know 5 pi over 3 is? Well, 5/3 is going to be greater than 1/2. Definitely greater than 1. Definitely great. It's 1 2/3, so it's greater than 1/2 because 2/3 is 0.6, where 1/2 was actually 0.6 continuing, but it's greater than 1.5. So it's greater than 3 pi over 2. So this one is in quadrant 4. And identifying what quadrant it is at the beginning is good because then we can put our values in as we put our signs in, SIGN, as we put our values in. Now, the over 3 rule, if it's a reduced fraction, which this is, 5 pi over 3 will not reduce any further. So remember the cosine is going to be 1/2. And what do we know about quadrant 4? What is positive? What is negative? Well, our x values are positive again, and our y values are negative. So my cosine is going to be a positive value, but my sine value is going to be a negative value. And if the cosine is 1/2, what always goes with 1/2? Square root of 3 over 2. All right, so now we can do our division. Negative divided by a positive is going to give us a negative value. And then we've got the square root of 3 over 2 times, keep, change, flip, 2 over 1. 2's cancel out. And we're going to end up with negative square root of 3 over 1, which is just negative square root of 3. So there's that angle, or sorry, there's that slope of the terminal ray, and then there's that slope of the terminal ray. So the big thing from this question is remember what that means. Don't read that and freak out. If you remember the slope of the terminal ray is nothing more than tangent of that angle, then it's easy. All right, so number 2 says explain why y equals tangent theta is always increasing for negative pi over 2 to pi over 2. So to do this, we need to think about the unit circle. That's not a circle. And that's not what I'm trying to do there. All right, let me get down here. There we go. There we go. All right, so if we're talking about the interval from negative pi over 2 to pi over 2, we're literally talking from negative pi over 2, remember goes down here. It's a negative angle coming from the x-axis down pi over 2. And then positive pi over 2, of course, is going to be straight up. So we're talking about this interval right here. That interval of angle. Now, what do you notice happens to all the tangent lines or all the terminal rays for this angle? Well, right here it's really, really negative. This is literally a negative undefined slope. And then right here it's still really, really, really negative, less negative, less negative. So what we're looking at is we're looking at what's the slope of these lines doing as we go all the way around in the exact same order that we're talking about here on our interval. As we start from looking down here and letting that angle get more and more positive, increasing from negative pi over 2 to pi over 2, the slope of this line is really negative. The slope of this one is negative, but not as negative. Not as negative, not as negative. Now it's positive. Right there with the blue line or purple line would be 0. There it's positive, more positive, more positive, more positive, and a positive undefined. So what's happening for those slopes of this tangent line, or sorry, slope of the terminal ray for that interval? What's happening to that slope? It is increasing for the entire interval. It's getting negative, less than negative than it was, less negative than it was, less negative than it was, less negative than it was, 0, positive, more positive, more positive, more positive, more positive. And this interval, remember, just tells us that all we're doing is we're starting here and we're going this way and we're analyzing what's happening to the slopes of those terminal lines. So, explain why. The picture's not going to be enough. So you're going to have to explain why. The slopes of the terminal rays or ray of theta increase as theta, I could write the symbol for that instead of writing it out, and as theta goes from negative pi over 2 to pi over 2. These slopes increase from negative infinity to positive infinity. So when we're looking down here, the slope is approaching negative infinity before it becomes actually undefined where we have the vertical line. But it's going to go from negative infinity all the way up to positive infinity as we go through this symbol, or through this arc of increasing the angles. Remember, that's all we're doing is we're just increasing the angle from negative pi over 2 to whatever angle this is, which is less than that, or sorry, greater than that. We're increasing the angle as we go, and what's happening to the slope as we increase that angle. The slope is increasing as well. All right, so number 3, consider the function f of theta equals tangent 1/2 theta. What transformation occurred from the parent function y equals tangent theta? Well, what's going to happen? Well, we're going to have a horizontal stretch by a factor of 2. Now remember, if it's inside, it's going to be opposite what we would think. Here we would think it would get smaller, but remember, since it's inside, it's going to be the opposite. Remember, when we go to find this period in part B, what's going to happen to it? We're going to divide by 1/2, which is the same thing as multiplying by 2. So that's where we get a horizontal stretch by a factor of 2. So what is the period? The new period is equal to the old period divided by b. The old period for tangent, remember, is pi. Pi and tangent and cotangent are the only ones that have periods of pi. All the others are 2 pi. Remember that. It's important. All right, and then we're going to divide by b, which is 1/2. So now pi divided by 1/2 is the same thing as multiplying by 2, so we're going to get 2 pi. So the new period for this thing is going to be 2 pi. Now, for which values of theta does f have vertical asymptotes? Now, we do not have a side-to-side shift, so that means we still have that key point, that center point right there. But now it's going to take an entire 2 pi to finish this whole series. And if this is the center, to get 2 pi, we're going to have to go this direction pi. So we're going to have a vertical asymptote right there at pi, and we're going to have a vertical asymptote over here at negative pi. So for which values of theta does f have a vertical asymptote? F has vertical asymptotes at theta equals negative pi and theta equals pi. All right, and then they want us to sketch a graph of f. Now, also remember, if they don't say in between a certain value, so that means we've got to continue this thing. And if we know that negative theta is where we have the first one, and we're going to have this every period we're going to have another vertical asymptote. That means that we're going to have a new vertical asymptote every 2 pi. We can actually write this in one statement and include every single one that there is. We can just do plus 2k pi, or k times 2 pi, or 2 pi k, whatever, multiplication, it doesn't matter what order you put those in. But all that means is we're going to take negative pi, we're going to add 2 pi, there's the first one. We're going to add 2 pi over here at 3 pi, that's the next one. We're going to add 2 pi again at 5 pi, there's the next one. So we've now listed every single vertical asymptote for this entire graph. All right, so let's sketch the graph. So the key thing is, don't get too tied up with it. We know that we're going to pass through right here, and we're going to go through that way. As we get over here to the vertical asymptote, it's going to take off and go vertical. So what you're going to notice is it kind of looks similar to a shrunk x cubed. It's going to look like an x cubed that's kind of been fenced in by your vertical asymptotes, and that's exactly what it is. So now, if we have a center point right here, where would our next center point that we can actually see on this graph be? Well, it would be at 0 plus the 2k pi. Remember, every one of these key points is going to occur that often. So if we wanted another center point to draw another period of this, we could go over here to 2 pi. There's my center point. Now, I don't have anything over here to draw because I'm running out of space, but I can still draw this one. So I can draw that half of that period. So that would be a sketch of f. That's all it is. If you absolutely need to, you can go over here and plug some values in and get some points. It's not necessary though. If they say sketch, they're literally talking sketch. Give me an idea of what this thing's supposed to look like. Don't give me one necessarily that has exact points that have to be in exactly the right place. The key points have to be, this has to be in the right place, and these have to be in the right, these vertical asymptotes have to be in the right place. But as far as that's concerned, the rest of this graph just has to have the right shape. So don't beat yourself up, and don't spend a lot of time trying to get points here to find exactly where this line goes, unless it's a very, very particular and you need to find exact points. If you don't, sketch it. And sketch it just takes the general shape. All right, so that's all of section 1. Hope that helped a little bit.